Hi, welcome back to Math 112. We are going to talk today about Chapter 9, specifically Section 1 of Chapter 9, which is all about conic sections. So this is going to be 9.1. And conic sections, before we get started on 9.1, I want to talk to you about what conic sections are. So we've been working with a conic section, believe it or not, all term long, and that is the circle. Conic sections come from envisioning a two-sided cone, like the one we've got here, and then you take a plane, which remember is just kind of like a sheet of paper that goes on in all directions, and you envision the different ways that that plane can intersect your cone. And so if you've got a flat horizontal plane, you get a circle. If you've got a completely vertical plane, you get what's called a hyperbola, and we'll talk about those in a couple of days. If you have got a slightly canted plane, you end up with an ellipse, which you probably know better as an oval, but the mathematical name is an ellipse. And if you've got a slightly canted vertical plane, you end up with a parabola. In each of these sections, we're going to talk about applications for these shapes, as well as their standard forms and their mathematical definitions. So let's start with the ellipse. We're not going to do much with a circle because we've already done that all term long. You've worked with circles, you know the standard form for a circle. You know how to find the center, you know the radius. So we're pretty much done with circles. So let's start with ellipses. And I'm going to go to Desmos here. Okay, and I'm going to open up a saved graph I've got here. Whoops. This one, maybe. Yes. So what I have here on my graph is an ellipse. Now, I just turned on this thing called definition for a reason. An ellipse is defined as the set of all points whose for whom the sum of the distance between 2 points that we call the foci is equal. So what's that mean? Well, so if we think about the length of this line plus the length of that line, that sum will be the same for any point on this ellipse. Okay? So that's the definition. Now, I'm not going to take you through the derivation of the standard form. If you want to look at that, it's in your textbook on page 581. What I would rather we do is that we be able to work with ellipses. So let's do that. I'm going to leave some points on here. And ellipses, by the way, come in two forms. They can be horizontal, like the one I'm showing you here, or vertical, like that one. We're going to live with horizontal ones right now. Give me a second. I want to make that a nicer number. Okay, that'll do. All right, and I'm going to pull this over so I can write on it. So some things we want to be able to understand about ellipses. Okay, I've got a center point on here, and we can talk about the center, and we will. And like a circle, the center will have coordinates h, k. All right, so this guy will be centered at the point h, k. Now, we're going to talk first about horizontal ellipses. So this is for a horizontal. For a horizontal ellipse, the distance between the center and this point up here and point down there, so this distance right here, is given the letter b. The distance between the other vertices, we call these vertices, is given the letter a. Now, notice that ellipses have two different axes. The longer one, whether we're talking about a vertical or a horizontal ellipse, the longer axis is called the major axis. The shorter axis is called the minor axis. Okay. The standard form for an ellipse is x minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. You'll notice the only difference between this, there are two differences between this and the standard form for a circle. You will always have 1 on the opposite side of the equal sign, but you will have some number multiplied by your x squared and your y squared. Okay, so now that we've got the basic standard form for an ellipse, at least a horizontal one, let's talk about a vertical ellipse. It's not very much different. The only difference between a vertical and a horizontal ellipse is which axis is longer, okay? So your key will be where the bigger number is on the equation. So let's do a problem here. We're going to start off with a relatively straightforward one. We want to put the equation, whoops, I don't want that color. (9x squared plus y squared equals 9 into standard form. The first thing we need to do is figure out which shape this equation represents. Now, we suspect this is an ellipse because we're in the ellipse section and we would be right, but here's how we know. We look at which variables are squared. So both x and y are squared. And both coefficients have the same sign. But they are different values. So we know from those two clues that we're looking at an ellipse. And what we want to do is we want to take the equation we've got and put it into standard form. For an ellipse. Now, in this case, we only have x squared and y squared. We don't have an x or y. So we know that h and k both equal 0. So this is pretty easy. To do this, all we need to do is get a 1 on the right-hand side. So we'll just divide through by 9. And we end up with x squared plus y squared over 9 equals 1. We can see that the number under the y is bigger. So we have a vertical ellipse. Right? And in fact, we could graph it. Centers at 0, 0. We know the upper vertex will be the square root of 9 or 3 units. So this is going to be 0, 3 and 0, negative 3. And we know the width is the square root of the number under the x squared, which in this case is 1. Square root of 1 is 1. So this is 1, 0, and negative 1 is 0. Okay? All right. So now let's try one that's a little bit more complicated. Let's put the equation x squared plus 2x plus 4y squared minus 24y equals negative 33 into standard form. Okay, so again, the first thing we want to do is look and see what kind of shape we have. We know both x and y are squared, and they're both positive coefficients. Both coefficients of x squared and y squared are positive, but different in value. So from those two clues, we know we are going to be finding an ellipse. And our general form that we're going for is x minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. Okay, so how are we going to do that? Well, first thing we need to do is go from x squared plus 2x to x minus h squared. So what we should be thinking of is that we are going to complete the square, and that's what we're going to do. Now notice I did a little work on the y before I set up my complete the square template here. I factored out the coefficient in front of the y squared. And that's why the negative 24 became negative 6. Remember, when you complete the square, you have to work with a coefficient of 1 in front of the y squared. Okay, so now let's complete the square. So I'm going to complete the square on each variable in turn, working on both sides of the equation. So I'm still going to do the same thing I always do when I complete the square, which means I'm going to take the number that is in the middle here, divide it by 2, and then square it. So I get 1. then that is what I add to the x. Now I added 1 on the left-hand side, so I need to add 1 on the right-hand side. I'm going to do the same thing on the y's. Take the number that is in the middle, divide it by 2, and square it. Which is going to give me 9. Now, I need to add something to the right-hand side, but I need to be careful, because what I really added was 4 times 9, or 36. Remember the distributive law. Okay, so now we factor the trinomials. X plus 1 squared plus 4 times y minus 3 squared, and simplify on the right-hand side to get 4. Divide through by that 4 because our standard form has got 1 on the right-hand side. So we end up with x plus 1 squared divided by 4 plus y minus 3 squared divided by 4 over 4 is 1. That will equal 1. Okay, so we've got a horizontal ellipse centered at the point -1, 3, with vertices square root of 4, 2 units to the left and the right of that center, and square root of 1, so 1 unit above and below that center. So if I were to graph this thing, start with my center, which is -1, 3, count 2 units to either side, 1 unit above and below, above and below the center, and sketch my ellipse. Okay, not too bad, right? Now, remember we talked about those foci? They're kind of important. In your textbook, they talk about a whispering gallery, which means that if you are looking at an ellipse, let's go back, let me get my Desmos ellipse here. Okay, here's the deal. Because of the way sound reflects, a person standing here at the focus, at one focus, will always be able to hear what the person standing at the other focus says, because anything that impacts this wall from that point is going to reflect into this point. It's physics. But this is what whispering galleries are made on. So if you've got a whispering chamber, that means that you can hear if you're standing on one focus, you can hear your friend stand on the other focus of the ellipse that forms that chamber, whispering, no matter what they whisper, no matter how softly they whisper, you can hear it if you're standing on the foci. So we need to be able to find the foci. In order to do that, we need one more characteristic of an ellipse, and that is this distance, c. And here's how we find that. So remember, the standard form for an ellipse is x minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. There's no c there. Here's where the c comes from. It turns out that b squared is equal to a squared minus c squared. Or the way I actually like to remember this is that a squared minus b squared equals c squared. Okay? So let's do a problem to illustrate this. And this is example 7 in your textbook, if you want to look at it. And it's on page 589. And here's what it says. It says, the National Statuary Hall Whispering Chamber is an elliptical room that is 46 feet wide and 96 feet long. To hear each other whispering, 2 people need to stand on the foci of the ellipse. Where should they stand? Okay, so let's think about what we've got here. Let's impose a coordinate system. Sorry, I don't like that. There we go. Let's make that a little more vertical. Okay, and I'm going to put one in here and one in here. What do I know? I know that this distance between these 2 things is 96. Now, by the way that I place them, you'll know that I put my center at 0, 0, which means that this distance, which is A, is half of 96, which is 48, right? And the other thing I know is the width of the room is 46. So this distance, which is B, is 23. Now I could put the thing in standard form, but really all I'm after, what am I after? I'm just after the location of my foci, which means I'm really just after this value, C. And remember that we know that C squared equals the bigger number, A squared minus B squared. So the only thing we have to be careful about with finding C is I'm working with a vertical or a horizontal ellipse right now. If you're working with a vertical, be sure that you put the bigger number first in this equation, because C squared needs to always be positive. So C needs to always be positive. Okay, so now that means that C squared equals 48 squared minus 23 squared. So C squared is 1,775, which means C is the square root of 1,775, which is about 42 feet. So our people need to stand 42 feet on either side of the center along the major axis of that room. Okay? All right. So we've talked about the meaning of the foci. We've illustrated how to find a foci, or the foci. We've talked about the standard form of an ellipse and how to go from standard form to expanded form. And that is the meat of this section. So I am going to leave you to work on the homework. And be sure and contact me if you have any questions. We'll talk again soon. Thanks.